Hello guys, this is Pytearcat and welcome to my another video, and today I'm going to talk about very special thing which is based on the calculation of tensors using the Python packages. Yes, if you are studying general relativity or cosmology, since you are visiting my channel, so I assume that you are working in cosmology or maybe some other related parts, but you want to encounter, you have already encountered with Einstein's tensor or Riemann or Ricci scalar, and you understand that as the number of indices getting more and more, calculating these objects are going to become very, very difficult. And therefore, we are basically today seeing some kind of packages which is written in Tensor, which is written in Python, so that you will be, you will see to amaze that how beautifully we can calculate these objects without making so much effort. But again, I'm telling you that using this package is not basically straightforward, right? So you have to make some adjustment, and also you have to familiar with the syntax that is going to used in Python. All right, so that's why I'm bringing this video, not on the data analysis, but most important part on how to calculate the tensor indices or tensor objects, or how we can manipulate some tensors or tensor indices using a Python package called Pytearcat. Yes, my dear, the package name called Pytearcat, and Pytearcat is available if you just Google it. And in this web browser, you have to just write this Pytearcat, and you can immediately come over here. You can immediately come over here. You can see that there is called Pytearcat. All right. So in this Pytearcat, which is publicly available, and you can find it in the GitHub over here. So you have to just Google it, Pytearcat, and you are good to go. So here you are, getting all the packages and so on. So what you have to first do is that you don't have to download anything unless you are a developer. You want to, implement some codes into it. You don't have to do anything. If you just simply use this kind of packages, what you have to do, that is I'm going to basically show you. But now, first of all, I'm giving you a brief review that what we are going to do. You understand that I'm talking right now, I talk about that Einstein tensor, which is g mu nu defined as r mu nu minus half g mu nu into r. And this is called your Ricci scalar, right? Ricci scalar and, sorry, no, Ricci tensor, it's not a scalar. And this is Ricci tensor, right? And over here we have a metric. And how can we define a metric? We can define the metric just by first defining a line element, ds square in cosmology, or in a Friedman Lemaitre metric in background for FLRW metric, we are defining is the time coordinate with negative sign, and there is a scale factor a square, which is basically time dependent, and some coordinate dx square plus dy square and dz square. So if I'm using the flat FLRW metric, so this is the metric that I'm looking for, right? And from here I can easily calculate, easily I can get the line element, because the ds square is defined as g mu nu, dx mu, and dx nu. So basically this coordinate which is defined over here, dx mu, is contracted with this metric tensor g mu nu. So g mu nu is a tensor rank 2, and it has the tensor elements. You can say that it is 4 cross 4. But thankfully, I'm choosing the metric in such a way that there is no any off diagonal elements, and so it has only 4 elements. So first element you can see over here -1, and then all the zeros over here, zeros, and then there is a square, and there is a square, and just put all the zeros over here, and you are good to go, right? So this is the metric that we are going to first of all have to give to the program, that I am choosing this metric, and now I need to calculate this Ricci scalar, because I am interested in Einstein's tensor, because after the Einstein tensor you can easily define you can work out the Hubble quantity or anything. If you are working with the Schwarzschild's metric, you can again calculate a lot of things. So therefore, in order to do anything, you have to first come up with the metric. So metric is most important part if you are doing general relativity, right? So this is the most important part, and it contains the necessary arguments, necessary hypothesis about the universe, that the universe is at the largest scale is flat, homogeneous, and isotropy. I've already described you the basic cosmology in my other videos, so you can look at that. through understand those parts. So basically today we are going to consider these important things. All right. So now what are the elements that we are going to get in the Pytearcat? So if you just go through this Pytearcat, you can, see some notebooks which is already given here. Let us say Einstein equation. So they have already shown you that how you can calculate the Einstein's tensor if you have any kind of matrix. But I have also tried it, but I find it a little bit difficult. Why it is difficult? Because I had to, I had to define my own tensor, and if you just look at these things, reading all these things and figure out that okay, fine, what is going on, it is basically time consuming. So I thought that why not, I'm just creating another video besides my data analysis video. So in order to, any beginner can, begin with the things that I'm basically sharing. So I'm telling you that this is a very important thing. You can go by yourself, or I'm just, going to give you the tour that how you can basically define your own set of tensor quantities. You can calculate the Riemann tensor and so on. So basically what is my objective here is, my objective is basically clear, and now I'm going to launch my VS Code. First of all, I launched my VS Code and I have just imported my file, my folder over here. So what you have to do is that you have to make sure that you are opening some kind of a folder. You can just make a folder. I have made a folder. The name is some kind of a general relativity, where I am just putting all my stuff over here. And then you have to first do is that you have to create a file over here. So you have to create a file which is called, let's say that once you have already done over here, you can just click over here and you can say that okay, by my file or my calculation dot. Now dot is necessary because which extension you are going to give you, because I am now working with the Jupyter. So I am just will give you IPYNB. So once you will hit the enter button, so the interface of Jupyter will come up over here. So first of all, in order to start with this one, what you have to do is that you have to make sure that which Python is basically over here, which Python version is installed on your computer. So you have to first install the Python version. So I'm using 3.12.3, and then you have to install pip install and Pytearcat. And once you will hit it with shift and enter, since it's already installed in my computer, therefore the requirements is already satisfied. If it is not installed in your computer, then you will not see this kind of output, right? So I'm going to clear the output, and here you are. So pip install Pytearcat, you have to install it, and then we are good to go. Right now I have installed pip install Pytearcat. In addition with that, I'm also using GIAPY. All right. So the manual is over here. They have published it in the Astronomy and Computing, the Pytearcat Python Tensor Algebra Calculator, a Python package for general relativity and tensor calculus. So you want to understand that how this basically have been mapped into the Pytearcat. There is a GR, there is a tensor. You can calculate all these things, all these stuffs. So these are basically most important part in order to get started with a GR. And if you have many, let us say that you are working with different kind of manifolds. So we are working with the FLRW metric manifold, which is flat and so on. So it's kind of calculating these objects are pretty straightforward, but not with all these things. So here they have already described that how you can calculate all the different tensors. For an example, over here there is an electromagnetic tensor F mu nu. So how you can do all these things, how you can define tensor of rank anything in no time. So that is what I'm going to basically talking about. So I have just installed this one, and now first of all I'm going to define my metric over here, that my metric is ds square minus dt square plus a square dx square plus a square dy square plus a square dz square. So you can choose anything and it will work simply amazingly, right? So my definition is already done over here, right? So this is for markup, this is not my code. Well, first of all, you have to import your Pytearcat using PT. So I am just using some shortcut definition of Pytearcat, that okay fine, I'm importing the Pytearcat, but I'm importing Pytearcat with a explicit definition that is called PT. And now first of all I have to define these coordinates, because T, X, Y, Z are the coordinates, and you have to mind it. When we are working with the spatial coordinates, these coordinates are not basically moving, right? So A is a function of time, x, y, and z are not a function of time. So you have to understand which are the function of time. So now here you can define that, okay, what are my function of time? So you can say that, okay, x is my constant. So how you can define your constant? All right, you can just say that x is equal to pt dot constant, and over here you can write x. Now, since these are my constants, so I have not, bothered about it. I have not, defined it. I just told you that. I just tell the computer that, all right, I have t, x, y, z are my coordinates. Therefore, I just point it out that, okay, because these are, objects, which is going to read by my computer. So there is a function called pt. All right, pt and small, and there were coordinates, and I'm just going to define some kind of a string t, x, y, and z. A is going to be a function of time. It's not going to be constant, right? So this is it. So A is a function of time because, over here you can see that this is t. T is not going to, do anything, and it's inbuilt that t, whatever you are going to do, they are going to take a derivative with respect to time and some called position. So you have this structure x mu. Mu is going from 0, 1 to 3. So x0 becomes t automatically, x1 becomes 1, x2 becomes, let us say, x1 becomes x, x1 becomes y, and x3 becomes z. So this is already defined, so that's why I have not done anything. I just tell the computer that A is my function of time, so pt dot function of time, and so on. It is already clear, right? So now in order to define this guy over here, what you have to do, you have to define my, all right, I am defining the ds. Ds is my some kind of a metric element, and you have to do the colon over here. And in this not colon, there is a apostrophe, or you can just say that whatever this notation means. So ds2 is equal to, so you have to write it over here, ds2, because it's already inbuilt, because that is what, computer is going to take you from here. ds2 is equal to minus dt square. In Python, if you want to take a square, you have to always use x double star, and there is a 2. So it will just tell this thing is that x becomes x square. There is a square, dx square, dy square, and dz square. And if you are in mathematics, usually we don't do this kind of thing over there, but in Python you have to understand that if I'm writing a1, they are to become object. They are not going to multiply it unless you have to this multiplication, right? You can just make it a1, but if you are not using this one, then it will just give you error. So therefore you cannot just write it anything with some kind of a space. You have to specify that, okay, what you are basically telling is, it is plus or minus or something like that, right? So whenever I'm just multiplying, let us say a into 2 plus 3, I have to write over here in Python a times 2 bracket 2 plus 3. All right, so this is how we are basically defining anything in Python. All right, so this is how we are going to define. And now therefore I am going to define my g mu nu, or the metric over here, that pt make a metric. So metric is over here, and there is ds, because in this function this metric is going over here, and then it will just simply tell you that what are the dimensions of the metric, and then it will give you the matrix itself. So let's just compile it. All right, so first of all, it's already in my computer, therefore it is just simply taking a little bit of time. I don't want, so I am just basically clearing my everything. And right now what it will going to do is, over here I have already done it, so let's just hit it. So once I have hit it, now you can see over here that it has already compiled. It has taken 1.8 seconds, and right over here you have, remember the time coordinate must be first coordinate. Yes, so you have to make sure that however you are defining your time coordinate must be always be in the first position, right? And the function at is already defined over here right now, because I have already chosen it. Dimensionality is 4, and the coordinates are t, x, y, z. The metric is defined successfully. So you have over here ds square. So all the elements that you are going to, all the output that you are going to see over here is purely in the latex format, right? And over here you can see that the metric, the matrix over here in the first element is -1, so everything is in diagonal element, and after diagonal elements are basically 0. So my metric is already defined. So what I am basically defined is that g mu nu is basically maybe 1, maybe 0. So g00 is 1, g11 becomes a square, g22 becomes this one, g33 becomes this one, right? So my metric is successfully done. All right. Now I can display it that, okay, fine, I have another way of, display this whole drama. I can say that, okay, since my metric is defined, and by you can just simply, because this is the most fundamental thing, so I can always take an inverse of this metric and I will always find g mu nu, right? G mu nu can be easily find out by just taking the inverse of this one. All right, so there is no problem. Therefore I can say that, all right, why not just give me that g dot display? So whenever you have already defined, because this guy over here has already defined in this one. So if I want to display something, so I will write g dot display and there is a bracket. But how you are going to display it? So if I am writing this way, I will tell that, okay, give me my covariant matrix. So these are alpha, beta, and this is basically give you the covariant matrix. And if I'm writing this one, g alpha beta, this is called contravariant. So if I'm writing over here, it will give me this one. If I'm writing g dot display, and over here, this one, this wedge kind of thing, and another wedge, and there is closed, the parenthesis closed, and it will give me this guy over here. You can see by yourself. All right, so let me just hit it. Wow. So you may see over here in a second that what is going to happen. So it has already taken the inverse. And if I'm saying that, okay, as list is equal to true, so it will just simply give me that what is my z00. Let me just say that, okay, fine, if I am using this one, you can see that it will become Kronecker delta. Why it will become Kronecker delta? You know that what happens if I have g mu nu and I want to calculate, let us say that g mu and nu. I will say that, all right, how can I calculate this one? I will say I'm going to take g mu and alpha, g alpha nu, right? Now you already know that what is g mu nu. I can just simply, because it's going to follow the summation g00 plus g11 and so on. So g00 it is -1, and there is also minus into -1, it is plus, and over here 1 by a square and into a square and so forth. So this is 1 plus 1, hence you have the another matrix. So that's why these components will become z00. First of all, this will become z00, and then so on and so forth, right? So if I am just using z00, I will get the element of 1, z11 I will get 1, and similarly g22. So you can whatever kind of display you want to choose, you can easily get it from over here. So I hope that this is clear to you, that how we can make these things. But the thing is that, all right, suppose that I want to make another tensor, right? So over here it is fine, because g is, whenever I'm just defining my metric, g can be anything. G can be either g mu nu, or easily it can be g mu nu, right? But let us say that I want to explicitly create a tensor, because it is the most important part. That how can I, because this is already inbuilt, right? They have already programmed it. But I really want to make my, let us say there is a cup, g upper tensor, and instead of these kind of notations, I want to create my own tensor. So how can I do? I know that because g mu nu, this is my already I've taken from the metric, but I want to create this g mu nu already. So g up will become g mu nu. This is what basically I want. So I'm going to, first of all, what I have to do is that I have to first define an object, and I have to make sure that this is a tensor of 2, right? So any kind of 2, it is not defining is that right now it could be any tensor, right? It could be contravariant and covariant. So first of all, I am defining my g up, and in order to make this object a tensor, I'm just using this one pt.tens, or sorry, pt.10, and first of all I am just passing this string gup, and then there is, I'm going to define 2. So now I have made this gup as a 2-rank tensor. All right, now I'm going to assign it. Now first of all, g is already there. You can see that g has already defined over here in such a way that it is containing your metric, right? So g is equal to pt.metric, and it has already taken whatever the elements and it has stored in G. Now G can be anything, this one or this one. But let us say that I have a covariant G. I want to make this G upper and storing G mu nu, because I'm making is GUP mu nu, right? So what I'm going to do now? I'm going to do a very simple thing. So first of all, I have already done defining G up a 2-rank tensor, and then I will say that, okay, since G is already there and G is basically carrying any kind of thing, let us say this one and this one, because G is an object which can have this one also and this one also this and this one, right? So I don't have any problem to do such and such one. So I just told you that, okay, since G was there, I want to take these elements into my GUP. So I'm taking these elements in my GUP, and then I say that, okay, GUP, this GUP element is going to become only contravariant. So it does not have any other feature. It will have only contravariant feature. And then I will just say that, okay, GUP, you can just display it. Okay, you can just say that, okay, it will complete it, and then you can just simply display it. You can just choose any of it. Let me just erase this one, and let me just say that, all right, don't go anywhere. I'm going to delete it, right? So if I'm just hitting it, you can see that it is now it shows me the complete, because I have already written over here gup.complete. So it will just tell you that in which seconds it has now completed it. You can see that the iteration per second, and now I got my gup tensor like over here. But if I will take this one gup like this one and this one, you will immediately see it will not give you, oh my god, it has not give you anything. Okay, it has given you this one, right? Because of this fundamental feature, that how we are going to do this one. So basically what we are importing the G in GUP, right? So but my GUP has already assigned like this. If I am doing this way, you will see over here that this is the matrix that you are basically going to get, right? So there is no problem with G. But again, once your metric has been calculated and you want to, let us say that I want to calculate another thing, A alpha, and let us say you have to use A of beta. So A beta could be, A is kind of matrix which is A is 1 0 0, and I want to make sure that I am going to make a covariant. So you have to you have to convert the indices, you have to raise the indices using this metric, right? So this is the fundamental rule. These two objects are different objects, and you are always using the metric tensor to lower or raise the indices. So I think this video is getting a little bit boring, right? Because you already understand these kind of things. So there are another object associated with Einstein's gravity. If you have action, you can just write over here T4x minus the square root of G is the determinant of G mu nu. Over here there is a Ricci scalar and there is some kind of constant. This is Einstein-Hilbert action, right? So R is your Ricci scalar, and which is basically made like this, G mu nu R mu nu. All right, and this is, sorry, R is the Ricci scalar and this is the Ricci tensor, RICCI, Ricci tensor. So over here I am going to assign, first of all I want to understand how this Ricci tensor will be calculated, because once I have defined the metric, these Ricci and these all the standard thing can be easily find out. You don't have to first of all you don't have to calculate the Christoffel symbol and so on. So just it's already there, right? So first of all, what I am going to do is that I want to see that how the Ricci tensor will look like for this matrix. So what I have done is that I'm going to use this important feature over here, that okay, pt dot Ricci. So Ricci scalar is defined as pt dot Ricci, and there is a box over here, parenthesis close, and I am storing it my RU. All right, bad name, but no problem. But the thing is that this is displayed over here right way. All right, because Ricci scalar is defined as this one. It is not defined like this guy alpha beta, but I'm going to, let us say that I want to see that what would be this object R alpha beta. Then how can I do it? Here you can see over here that R alpha beta, we have, first of all it has calculated this one, and from here this has calculated R alpha beta, and we have, so this is basically the Riemann tensor, and over here this is alpha beta, and for this calculation it has already calculated this gamma alpha beta and so on. So this is not this is the process that after which you can get. So first of all, you have to make sure your metric is already defined, and then it will calculate alpha mu nu, and then it is calculate alpha mu nu lambda, and then it will calculate r mu nu. Once it is defined, it will calculate this r, right? So everything is starting from here. So this is the tree that you have to understand. All right. So these are the, so here they have defined these two things, alpha mu nu, all right, and this guy over here. Two things are already defined, so that's why they have already written which things you want to take, right? And over here you have Riemann tensor and Ricci tensor, and then your Ricci scalar. All right. Okay. So I'm over here. So if I cannot, if I want to display that, all right, just like we have done, can I do like this? Can I do like this? Like this? Okay. No, you cannot. This is the beauty over here. You cannot. This is the nan. So if you are not following the way they have already, give you, because they have made an object like r mu nu. They have not made any object like this or like this. If you are trying to specify any other thing, then it will give you that, okay, not available, nothing, it's called infinity, all right? So therefore, I have to construct an object to calculate this one, right? So let me just first of all fix it. Okay, ρ has the Ricci scalar defined as r mu nu, but I want to calculate r mu nu. Why? Because there is called a Gauss-Bonnet theory. In Gauss-Bonnet theory defined by G, and which is like this, r square minus 4 r mu nu, let us say r mu nu, if you are come across this one. And there is another thing like alpha beta gamma delta and alpha beta gamma delta, right? I want to calculate this object. What would be this one? So if I am just if I'm just using my hand, you can see that r is a scalar, therefore all this thing has to be scalar, therefore G is now becoming a scalar. So I will just get not a matrix but only one particular answer, right? For a scalar there is not too much problem, but the problem here is that I have this object, I have this object alpha beta gamma delta, but how can I make this object and this object and this object, right? So this is the game that we are basically constructing that. Okay, fine, I want this one, right? So in this Pytearcat, if you want to calculate G alpha beta, the Einstein tensor r mu nu minus half G mu nu r, it is pretty straightforward. You don't have to do anything. You just make sure that G is there, and you can just write that pt dot Ricci, right? pt dot Riemann and bracket, and you are good to go. pt dot Einstein and so on. You are good to go. You don't have to do anything, right? But I am going to construct from the scratch that I want to construct my G alpha, sorry, my Einstein Gauss Bonnet. So for that, I have to construct this guy over here, r mu nu. In order to raise the, and I have this r mu nu, right? In order to do it, I'm going to first write over here r mu alpha and nu beta. And there will be alpha is contracting this one, beta is contracting this one. So my ρ has this guy. I have my metric, which is just like gup, and there is gup. But you have to, whatever you have chosen over here. So for simplicity, I'm not writing over here mu and so on. I'm going to use A, B, C, and D. So let me just erase this guy over here so that you can understand what I have used over here. So I will write over here that, okay, I have GAB, GAB and C and D. My bad. C and D. So this will become B and D, right? So B and D are going to contract it. So one thing I must tell you this one, that whatever you are using the indices, let us say this is A and B, sorry, A and C, it will become A and C, right? If I am using these indices or this object over here, you have to make sure that you are, actually using the same element or same name everywhere. All right, you don't have to clutter it, because it will first take that string to follow that. Okay, basically what you are doing, where your element is storing in the matrix. All right, so this is basically too much important in order to make sure that you are following this routine, right? So over here, what is basically happening? The happening is the multiplication. This is multiplying, this is multiplying. So multiplying here is basically giving you like Einstein summation. All right, so there is nothing else. So what I have done over here, that I am just I am, constructing this guy over R mu nu. So first of all, I am again considering I am considering RUP, R upper. R upper means that I am considering R mu nu right over here. Let's say that it is two rank tensor. Therefore, value that I am adding over here, that GUP, right? So first of all, I am not assigning right now. I am just first of all calculating what is the calculation. I am saying that, okay, G mu alpha and then again G nu beta and then R alpha beta. So this guy over here, because cup has, once you have constructed a matrix, you can always change. Once I have constructed that, okay, this is my matrix, right? I can change, I can use any name. So how I can naming it? Let us say that I want to specify indices because it's going to do the summation. So I have to use this mu and alpha. So I will write in this way. I will say that this is my cup GUP, and this one, first of all, go and take mu over here and then comma. This one is also contravariant. Go like this and this sign. This is how I have done it. So this sign, or maybe just only one sign, one apostrophe, and there is up. And then I have already defined RU. RU is basically R mu nu, right? And therefore it is basically this guy over here contracting with alpha and beta. So R alpha and beta, and R alpha beta is like this. So I have RU and then this guy alpha, whatever the name I have written, and then beta. Done this. And there is a multiplication sign everywhere. If you are not doing the multiplication sign, then you will get an error. And then what I'm saying is, okay, whatever that value that you have calculated, I have to again this making object must be a tensor. Value is not my tensor. Just I'm storing it. But RUP is my tensor. Tensor of rank 2, because R mu nu upper is a rank 2 tensor. So R upper, assign whatever the value that you have calculated and then assign in this way. R Ves mu and Ves nu, right? R of factor, just whatever that you have done it, factorize it, complete, simplify. Again, I want to simplify it and then display it. Display like this. And as I'm displaying it, you will see the beautiful thing over here. Now over here, you can see that it has now inverted. So R mu nu I have successfully calculated. So basically I have made, which was not existed before, but using the other objects I have created. So in order to make a tensor, you have a very good knowledge how to play with the indices, because this is basically what you are doing over here. You are not doing the calculation, you are not doing the covariant derivative or differential equation. But again, if you don't know how to raise or lower the indices, then you are not going to survive it, right? Or you may do it wrong way, right? So over here, if I am just saying that, okay, can I get like this, you will see that no, you cannot get like this. All right. So over here, it is all right. It has already given me this one. And let us say that if I am doing this way, what can I get? Yeah, you can see the very incredible thing. This is basically, is it? Yeah, is it? Because I am because GUP can be manipulated in any way, right? And R covariant is already done. Therefore, before it was not possible to make any kind of other thing, right? Then, but now with, as I have already defined this way, then I can calculate anything. So RUP can be defined. Now RUP can be defined in this way. RUP like this, that okay, fine, mu nu. RUP can be like this, mu nu. RUP can be mu and nu. So now I have objected. So that is the flexibility that you get, right? So if I'm just using this guy over here, and this is always possible because you can see over here, this is possible due to the only one thing is because of the metric, right? So this is a very cool thing about this whole tensor quantity or whole Pytearcat, right? Now let's proceed. Now I have Riemann. Now I am trying to construct this RABCD, right? Because this Riemann is defined as like this. As you can see the structure over here. This is defined as R alpha beta gamma delta. But I require, because in Einstein's Gauss Bonnet, I require this A, B, C, D. So let us say that I have required alpha, beta, gamma, delta. So, but this is my, this is what I got. So I have to do, I can just write this way. Let us say that this is alpha and mu. I will take this indices upper. You have beta, gamma, delta, right? So I have to make this one. I have to see over here. That is how you can, raise or lower the indices right now. So I have this guy over here as already calculated this one. I have this one. I can easily calculate this guy over here, right? Let's see. So for this one, I have pt.Riemann and there is a bracket and it will show it. But if you will see that, okay, fine. Can I have this guy? You may see that, yeah, I can have this one, but you can see over here, there is a nan. All right. So you are not going to get it. And now since this is not a matrix, therefore they will not, going to show you in kind of a matrix because it will be very huge matrix and so on. But over here, you have this definition, right? So how we can go from this one to that one? Let us just remove this one. You already know how we can do it. GAB, this one. So first of all, I am defining my object RC. Here is my object RC, as it is containing 4 indices, 4 tensor. I have GAB over here, and then I'm multiplying with G. This is R because R is where I am inputting everything, right? This is my input, correct? So R is where I am doing everything. So R is over here defining it. Then I'm going to assign whatever that it has calculated, and I'm assigning like this. There is a factor complete and so on. And immediately I will see what? I will see, like, maybe I'm going to see some magic, right? So here it is immediately calculated R, A, B, C, D, and now you can see over here. Cool enough. Now, like same way, can I get like this? Because I have already done it. So it should be, yeah, wow, that's great. It is exactly same as what it previously we have done it. But can I also get this thing? If I can get, because I have not yet tried this one. I have also learned it just day before yesterday. And so I thought that, okay, fine, not, I'm just to calculate this one. Oh my God. So I don't have to, do anything. I just have to define that like this and everything is boom. So you know that once I have already inverted or raised or lowered it, so it already understands what it has to do, and boom, it has already done it, right? But still I'm going to, show you that, okay, how we can let us say that RC is something which is 4 indices, and I have already assigned it that how it will, how it will contain all the value. It is covariant, right? Over here, I am going to, make another indices from, because RC is my lower indices, right? So RC is lower because it is defined, RC is defined as alpha, beta, gamma, delta. Correct? But I want to define as alpha, beta, gamma, delta. So I will do first of all alpha, mu, beta, let us say I, gamma, j, delta, k, and r, mu contracting with this guy, this guy, this guy over here, and there is k. So now I have already defined it, right? RC is already defined. This is just display. Don't go for it. RC is already over here, right? And then I'm going to simply make it like this, product, all the uppers, and there is a RC, all right? Because I cannot use R over here because R has some restriction because it can have like this. I'm using this guy over here. So I'm just telling you that how we have got it. And boom. You see over here, the previous answer is simply matching whatever you have done right now, right over here, correct? So I have already made this RCT. RCT is that R contravariant, right? So R contravariant, come on, hit it. 2602 and boom, a to the power 6, you have also got it, a to the power 6. So now I have calculated everything, and then there is a Ricci scalar, and for Ricci scalar, they have already put it just like S over there. So there is a Ricci scalar, pt.Ricci S, and over here, if you just hit it, you will get just only one solution because it's not a tensor object. So you will have this particular this one. So you can just simply see 6a d double dot. So this is basically d2 by dt square a of t is telling you a double dot plus a dot dA over dt, and there is a squared over a squared, right? So this is what you will get. And if you don't know how you can manipulate with h, you can simply say, because h is equal to a dot by a, this is how you define h dot becomes a double dot over a minus a dot square over a squared. S dot is a double dot by a minus h square. Therefore, a double dot by a is equal to h dot plus h square. So this would become, if I'm dividing, this guy would become 6 a double dot by a plus a dot square by a square. And you will get a double dot by a is h dot plus h square plus this was basically h square 2h square. So now this is your R. Right, so this is what we have got. If you just see the textbook, if you don't trust on this computer, you will see the exact thing with ds squared is equal to dt minus dt square plus a squared dx squared, right? So now it is complete. So now I got everything, but now my job is to calculate what? Calculate this guy over here. R square, Ricci scalar, I'm to multiply it, minus 4 r mu nu, and plus r a b c d. So right now, in textbook you will say that mu, all the Greek indices will run from 0 to 3, and all the letters, English letters, will go from 1 to 3. But here the system does not bother about that. Whatever your indices you want to use, we are not, there is nothing like that. Okay, fine, it has to go like this. It is not inbuilt over here. You can just use any letter, as long as you have to, be very specific that which indices you are basically, contracting with which, right? Otherwise you will be wrong. The result will be wrong. So now what I'm going to do is that once I have calculated everything, therefore rs for Ricci scalar, and then I'm multiplying it, power squared minus 4. There is ru, because ru is what I have already defined it using Ricci scalar, and then there is Ricci covariant contravariant scalar r upper plus RC the lower, and RCT is the upper. I also can use this one RCT and this guy over here, and then RC, and again I'm going to use this guy. So I don't have to do all the calculations again and again, but with this I have to use ABCD, this ABCD. So everything is basically intact, and then it will become a Einstein summation. And over here EGB, then I simplify, and hurrah, because your G is the scalar quantity. So what you will get over here is following. You have got this 24, incredible. If I just do it by hand or some other thing, it was kind of devastating, but here I got it. I got the complete numerical value what it is, and that's done. So it is basically giving you 24 d a dot square times a double dot over a cube. Now if you just use it, and it will become 24 has something like s dot plus h square, right? So this is very incredible, amazingly incredible, right? So why I'm using this one? Because I just want to tell you that how you can make your own tensor object, how you can do the difficult calculations, mainly the objects that I am trying to calculate it. So that's why I have taken a difficult example where a lot of indices are involved. I have also, because it's also related with my research work, my present research work, that's why I've also calculated it, and I thought that what could be the best way to calculate it. So Pytearcat is kind of incredible to do these kind of calculations if you are using Python. In my later video, what I'm going to show you that there is a mathematical file which is again too impressive. It is fast, and it can calculate all these things. Like for an example, you have some kind of integral d4x minus root g Lagrangian, right? R over 2, let us say pi square. I want to take a variation ds is equal to d4x square root of minus g r and something like this, and there is a delta. Now this program is not meant to do this kind of type of calculations, but there is a mathematical whole packages where you can do all these things, tensor manipulation, tensor calculations, even if perturbations, we're taking a variation. So I will just also make another video on those things, that how you can do this thing systematically, right? I will just do whole mathematics, you will see it and you will learn exactly what I am basically doing on the real time. So I hope that this video is making sense. All right, before I'm just tell you that what you will get if you are calculating the Einstein tensor over here. There is an Einstein pt dot Einstein right over here. You just have to do nothing, p dot Einstein. It will just simply tell you, oh my god, this is the Einstein tensor, right? Just hit shift and enter, and what you will get is following. Oh my god, boom. So here you got the left hand side of Einstein's field equation, which is g mu nu, and basically you will have to invoke some kind of meta quantity, which is t mu nu, and t mu nu is basically defined as minus 2 over square root of minus z. There is an s for xn, and delta of, if I'm just varying this xn, delta s over delta g mu nu, you will create a stress tensor or energy momentum tensor of this object, right? For the perfect fluid, which we are basically using as T mu nu, which is already defined here, rho for energy density of that component, that is a pressure for this one, u mu u nu plus p g mu nu. So right now u mu is not defined. You can just define it. First of all, u, basically I want to assign pt dot tens, and there is 1, right? And then you can say that, all right, I want to assign it. Assign what? So over here you have to assign it, because whenever you want to make a vector, you have to just define it in the array, right? So this is basically you are making an array. Once you are done, because you are assigning, you are constructing u mu, you can say that, okay, comma, and there is mu, right? This is already assigned. So you have now assigned, and you can display it, u dot display, and so forth. And if I'm just hitting enter, you will see the boom, right? So you have now constructed that contravariant of u, right? And once you have contravariant of u, then you can easily assign that, okay, fine, what happens if I have u this one? But if now once I have just assigned u contra, if I'm hitting this one, it will give me 9, right? It will not able to do this guy over here. So basically what you have to do, you have to again create an object. You already know how to create an object, because you have to do is that, let's say I want to create this one, I will have u new. So g00 u0, because u0 has just only one element, right? And then you will have minus 1. So u0, now you have already calculated. So now here it is. I'm just creating t mu nu right over here, tensor 2, and there is rho plus p, u mu, u nu, everything is contravariant. There is a pressure term, which is scalar term, and then g mu nu. Once you have already done it, you assign it whatever the value you have over here and simplify it. And when you are going to hit it, boom, and you have created the so successfully the matrix. So first of all, what you have defined over here, you have defined a simple order G, then you calculated Christoffel symbol, you calculated Riemann tensor, you calculated Ricci tensor, and then you calculated R, Ricci scalar, you calculated G alpha beta, you defined some T second order tensor, T mu nu, and once it is done, G alpha beta is some constant T alpha beta, right? T alpha beta, you can easily calculate it, because you have to again do the following: alpha mu, beta nu, mu, and nu. Once you have already defined it, just do it this one, and boom, whatever you want to calculate, it's on your hand, right? So this is how this manipulation happens. And if you want to work with black hole and so on, so this thing is very handy. And if you want to calculate any kind of object, if you're in MSc, you are first year research, or you are in research, or if you really want to understand general relativity and you want to afraid of calculating these objects by your hand, this package will help you a lot. So if you are using in your research paper, cite my video, cite the first of all this Pytearcat, which I have already shown you in the video. Their link is there. So they have already described that which paper you have to cite it specifically. So you have to cite that paper and make it transparent, and also share my video with your friends, because it's important. You have already understood, as I have made it public, so you can also share it with your friends, because it's going to help you a lot, and your colleagues and so on, right? So see you later, guys. And I will also make another video on data analysis, so please keep check whatever I have made some video on data analysis. optimization, Python, and all these things. So in this channel, you're going to get a lot of things free of cost. This is the Melado Cap signing out.